Hello and welcome back to Calculus 3. This is exam 3 review where we are going to focus on chapter 13, which is multiple integration. Everything from this chapter is important if you are looking to figure out the area or volume or the fourth dimensional entity, right, that you need to figure out. So let's see the way integrals evolve from Calc 1 all the way through Calc 3. The most important part that we are going to first see is that in the definite integral a to b of f of x dx, which was calculated as the antiderivative between a and b, which is f of b minus f of a. So this is the part of the fundamental theorem of calculus, and calculating this definite integral shows up many times in our integration. So now what happens is you assign a meaning to this, because if this is this function is above x-axis in its entirety, then this particular integral will calculate area under the curve. So I will have some kind of a function that is strictly above x-axis, and that function is f of x. In this case, right, between a and b, in this case, area is equal integral a to b of f of x dx. So we see that our definite integral computes the area. Now, in case that your function dips below something like that, right, and you are again on interval, let's say a to b for this f of x, well, you have this red part over here, which is the dangerous part. So I'm going to come up with C and D limits here. And this particular region, to find the area, will have to be calculated with 3 integrals, because I do have 3 different regions. Now, integral from a to c of f of x is above x-axis, so I don't have to do anything with that one. But that next integral is integral c to d of f of x dx. That one is below, and that will produce the negative area, so I must place these absolute values to make that number positive. And then finally, integral of d to b of f of x dx is also up above the x-axis, so we don't have to worry about it. So that's the story of Calculus 1 and Calculus 2. The rest of the calculations that you have are just different techniques of integration. We have basic integrals, we have the u sub, trig sub, partial fraction decomposition, by parts, right? All of those are just different ways to take the integral, but conceptually you are not learning anything new about the integral, right? And you continue learning about integral and dimensions when you hit Calculus 3. So now, well, first of all, there is this one thing that I want to mention from Calculus 2, first lecture, 6.2, says that area between 2 functions, and this plays the role in Calc 3, area between 2 functions, function f on the top and function g on the bottom, is given as integral a to b, which is their intersection, of f minus g dx. So now we are already in Calculus 3, where I can say that I can calculate the area if I go a to b and then integral, so double integral now, of g to f of dA. Right? Now this dA could be either dx dy or dy dx. That depends on the geometry of the problem. And if you take a look at this, going back, the reason why I started with fundamental theorem of calculus and definite integrals, observe that you are subtracting top minus bottom when you have the calculation for it, right? So this is why I can substitute this with another integral. Because when I integrate number 1, that it's here, we will have, let's say, integral a to b, and you will have y computed between g and f, right? And that's just going to be f minus g, top minus bottom. So actually becomes this step up there. So now we know that area can be computed either by the single integral. If you have one function, then the bottom function is the x-axis. If you have two functions, then you have f minus g. Or you can put those f minus g in the nested integral, right? So the second integral for double integration, and you will find out also the area of the same doing that. So let me just write that this could be understood as a formula if you want to, but integral ab, integral g of x to f of x of dy dx is actually the same as just writing integral a to b of f minus g dx, because that's actually the next step. So we can have that. So we can use single integrals or double integrals to compute area. But now what I'm going to do in the next step is to introduce a function within the double integral. So if I have a double integral that we had before, which is a to b and then g of x to f of x, and I introduce some kind of a function here, say age of x, y, and then I have my dy dx, well, now this thing calculates volume, because I have 3 dimensions. There is a dimension age, which gives me the height, and then I have these 2 dimensions that give me the base. So now this is a 3-dimensional entity, and that is called volume. Now what I can do, now what kind of volume is this? Well, this volume is when your bottom is flat. So flat bottom. For instance, that printer has the curved top, and there will be some kind of f of x, or age of x, age of xy, describing that wavy, curvy top. But the bottom of that printer is flat, and that's why this double integral works just fine. But if I want to have an object that it's curvy or wavy on the bottom and on the top, well, that calls for the 2 functions. And that I can do the good old way of top minus bottom, just like we did for the area. Or I can come up with a 3rd integral where I'm going to place those 2 functions and say the bottom part is described by this equation and the top part is described with this equation. So I can now have upgrade into the triple integration without anything inside, because I'm looking for volume, and it's already dx, dy, dz. So now I have numbers on the outside, function in terms of x. Oh, if I'm going to use x, then I can go dz, dy, dx. What was that sound? Oh, that's the erasing sound effect? Okay. And then f of x, and then I have g of xy and f of xy as the most inner, and that would be top of the object, and that would be the bottom of the object. So guys, you have a project question that you are supposed to solve, which is an egg question, right? And for the egg question, you have to model, right? When you trace the egg onto the paper, right?
How are you going to trace the egg on the paper?
It's a head.
Just hold it for
Problem solved. It's definitely an egg. All right, so
naming has power, I guess. Sure.
do you see this? End of discussion. All right. It's a deformed egg.
I'll accept that.
Yes, and there will be a very peculiar chicken coming out of it eventually.
What's on the inside? Okay. So my food? I don't know what's on the inside. Yeah, my food.
So I can like easily break it in half. Is that it?
Oh,
It's an egg shape.
you get to eat protein, which means you.
What?
What?
So you cook the egg first.
It's an Easter egg. I said that. I wasn't paying attention.
We didn't answer it.
No,
Why? How will you know?
because I'm just telling you, you cook the egg, then you can decorate egg, make it into face or whatever. But you trace it on a paper, guys.
Why
The fat part of the egg could be either a sphere, right, or something like that, and then the top might be the parabolic, or the bottom could be elliptical, right? So you see what fits the best. But you will be cutting, right, the equation in half and dealing with the two parts. But now look, if you go into the triple integral, then these two functions will fit on the most inner integral, with the middle being empty.
So to do a triple integral, you just need
It said use the double integral, but whatever.
I don't understand how we're supposed to get the solution.
You trace on a paper.
Yeah, but then
You have the points. You figure out. You'll figure it out. If you haven't.
do I really?
You apply algebra on it, yeah. Yeah.
What's that?
Exactly.
Be right back to you. Oh, what? A beer?
That's
a beer too.
It's a
Not a beer?
beer or beer?
Yeah, we all got excited and then just ruined it. Well, everyone is excited here because you are drinking.
Now she's outside.
Because you can put inside the double integral f minus g.
I don't, what? But
Yeah.
can we also theoretically use it easier for us?
Yes. Your next step would be the double integral that I asked for. So, what?
Can you use a single?
Yeah. But
You don't care, probably, but I'm just so you know.
no, he's
From Calc 2.
rotation, of course. Yeah, the disk method and the shell method. Yeah.
You pretend I didn't ask that.
But it's a calc. It's Calc 3, so, and Ryan is too advanced for this class. So anyway, all right. So now that we have the all of these integrals ready, we have to understand that we can change the base coordinate system. So the base coordinate system is generally x, y, z, and we can take the x, y and replace that in a 2D realm with polar coordinates. So now we have the integral that was given to us in the double integral, that was given to us as dA, and the geometry will decide whether you are going to go double integral dy dx, or you're going to go double integral r dr d theta. Now, this was the double integral. This was 13.3. Once you move into the triple integration range, you will have the triple integral dv. Again, geometry of the problem will split this integral now into 3 different categories. You have the category of the triple integral, which was dz, dy, dx, which we call rectangular integrals. And then you have the cylindrical integral, which is the triple integral that has dz, r, dr, d theta. And finally, spherical integral, which has that very long string of rho squared sine, phi, d rho, d phi, d theta. So geometry of the problem. Now, what do I mean geometry of the problem? If it has sharp edges and rectangles and triangles and stuff like that, like the planes and things, you really don't want to use spherical integral for that, right? If it is circular, right, and in terms of the type of a cylinder, or if it's parabolic in shape like umbrellas and so on, then you are using cylindrical. And if it's a sphere or a portion of a sphere, the cutout of the sphere, you can use spherical integral. Now, conversions between these are important because in some cases the only way to solve the integral, since you don't have access to technology when you're doing the test, is to convert the integral into the realm of the other integral. So generally it is evil integral was given as the xyz integral, and then you swap that into the one of the other two. Now, to be able to swap that, you need to have knowledge of the conversion formulas, right? And that is generally that for polar domain, right, to go into cylindrical coordinates, because z is the same. For the polar domain, that is that your r squared is equal to x squared plus y squared, or r is equal to square root of x squared plus y squared. Do not underestimate the power of that conversion. The evil integral, I don't care how many integrals you have, if you have something like this under the integral, and let's say you have this, and then there is more stuff over here, blah, right? This thing is actually equivalent to just this. Just that. That's it. Because you already had the square root over there. So you can see that this crazy looking integral that was definitely some kind of trigonometric substitution, right? If you want to push it, is going to be very simply just integral of single r if you are changing it into polar coordinates. The same is going to happen with the spherical integrals. We saw that 2 days ago when I said, all right, it's time to change to a spherical integral. So you have square root of x squared plus y squared plus z squared, and all of that was just a rho. Now rho is the radius, plays the role of the radius, right? So for polar coordinates, your radius is lowercase r. For the spherical coordinates, your radius is lowercase rho. But it's the same thing. We could have used the same letter. I really don't know why. With this particular, I haven't seen it in any other book. It's just this book is using rho for spherical coordinates. Why? I don't know.
But
anyway,
if we want to write it with r, just to simplify our lives.
It's fine. I don't care.
Because sometimes I get rho.
How do you get rho and phi confused? Rho, phi.
Well, because like when you were sometimes you write your
sometimes you give rho a tail.
Rho always has tail.
Well, no, I know rho has tail, but if you go back to your notes, it comes.
No, but like an extra tail above it, like a sideways tail. So a ponytail. Yes.
Oh.
Someone would actually have to draw that or find it in my notes, because
I'll do it.
Yes.
Okay.
Conversions. So, conversions from polar into rectangular, rectangular to polar are well defined from Calc 2 through Calc 3, and we know that we have the conversion x equals r cosine theta and y equals r sine theta, and z is equal to z for cylindrical coordinates. So yay, we're done, right? If you carefully looked at the lecture and read it on the spherical coordinates, the book tells you converting this is good luck, right? That's all it's good luck. Because when you look at the problem, right, geometry will guide which trig functions will be involved, and it changes with the geometry of the problem. So there are no established formulas that are one size fits all to convert rectangular into spherical, right? So that is the much trickier business, which is why you are going to find that the vast majority of the problems you see only have the square root of x squared plus y squared plus z squared. The others are not impossible, it's just they require a good understanding of trigonometry. And that's, something that, you take your time to figure out. Yes?
We have like the cylindrical coordinates, so that's just dx and y.
dA is going to be appropriate to your application, because it's dy dx or dx dy for rectangular coordinates, but in the second integral you see there on the right, that whole dA is r dr d theta. So on the left hand side, this puppy over here is either dy dx or dx dy. On the right hand side, this is definitely r dr d theta. So that string has to be known. You have to know that one 100%. Now, you have the string for spherical, which is that, and then dz in front. For cylindrical, and for spherical you have the rho squared sine phi d rho d phi d theta. Now, to set up integrals, you absolutely must draw the region. The region can be very tricky, or it could seem that it's easy, and then it turns out to be wrong. Let me give you the best example. I actually worked on this earlier today. The best example of the dangerous one would be circle. So if you are setting up integrals in the circle, you have a choice of cutting dx or dy and so on. Now, let's say that your problem is asking you to integrate half a circle. So all you have is the upper half that you have to deal with, and let's say these limits over here are negative a and positive a, which would also give you the top over here is a as well. Now, the question is, when I write the double integral, right, and maybe I have something over here or not, doesn't matter, I have dA, and that dA could be either dx dy or dy dx. You get to pick which one of these two. In some problems, both of them work. In some problems, one is easier than the other. And in third type of a problem, one is impossible and the other one is the only choice. Well, this is that third type of a problem, because you are not allowed to have one of these as the outer, and that is dy. Exactly. Because look what happens, guys. I am going to write this function here as y is equal to the square root of a squared minus x squared, right? That's the formula for that line. What happens if I write dy? If I write dy as the integral, so that means it will be dx dy like this. Let me show you why and how is this so wrong. On my diagram, dy on the bottom will start at 0 and go all the way to the top to a. The functions over here have to be x equals and x equals, and then there is, but it's the same. It's the same function. You see this side touching the function, and this one is touching the same function. So over here, I'll have square root of a squared minus y squared, and over here I'll have square root of a squared minus y squared. In Calculus 1, you learned a theorem which says that integral from a to a, whether it's a function or a number, of f of x dx is equal to 0. Why? Because fundamental theorem of calculus commands it on the top line. When these two things are the same, then these two things are the same, then these two things are the same, and when you subtract the same things, you get 0, right? So, going back down here to set up this integral, I cannot put dy in a way that this will fold on itself. Same reason why I cannot set dy inside x squared. Because your bottom would be root y, your top would be root y, and right? L breaks loose because it's touching the same line. So it is wrong to put dy in this case. Therefore, we will abandon the dy on the outer as no, it cannot be used, so nope. And we will actually set up the integral the way it has to work out, which is dy dx. Now you will notice that the x, dx one, right, the one on the outside, goes all the way from negative a to positive a. And the bottom is 0 because for dx, right, dx is going to touch the bottom. And then touch the top of the function, which is a squared minus x squared. And lo and behold, we have the integral set up. Another issue that I've seen throughout the years is you not working well with circle to set up the integrals. The circle has a symmetric equation, and technically the equation solved for x or y looks the same. So if I am dealing with a circle which is cut with x, the top equation is y equals square root of radius squared minus x squared, and the bottom equation for that circle is y equals negative square root of r squared minus x squared. Now if I have the circle cut vertically like this, actually I should draw this in the middle. If I have a now I can't have a circle. If I have a circle cut vertically, then the equation on the right is x equals square root of r squared minus y squared, and the one equation on the other side is negative square root of r squared minus y squared. So in this case, right, you have that. So the equations are symmetric, but you need to know how to portray every single one of these. Now please note that if you have a quarter of a circle, this equation over here is at the same time y equals square root of r squared minus x squared, and x equals square root of r squared minus y squared.
So is that like the z equals?
Well, see, this quarter circle is both of these equations at the same time. So now you have to go into the problem and decide which one is better, right, for you to use. And that goes for all 4 quarters of the circle, because obviously the equations intersect, right? They don't line up because they're 90 degrees offset, but the in each quadrant, both of the equations apply. So for this particular quadrant, I can use either dx or dy. It doesn't matter unless the rest of the problem is pushing one more than the other. I think that's it for this. Examples, yes. So
it's 2 pages. I know you explicitly said not to.
but you
fine.
Yes.
If I also do it, never stop. If I don't work ahead, I'll fall behind. It doesn't work out for me during the interview.
Oh, wow. I just found an awesome question for the exam.
Ooh.
Actually, kind of want to.
What number is it? What?
Also, can we get our class preps up till now back before the
Yes.
What?
He disagrees with you.
Oh, I can talk whatever you want. It's a free country. Sister, yeah. How do I draw this? So. This is the review, problem 34.
Is this from what section?
Review session. So after all the sections at the end of the book, there is a review.
Awesome.
You're welcome. So now let me try and draw this thing somehow.
This already I'm already nervous. Oh boy. A watermelon slice?
It looks like a potato chip.
It's 2 potato chips together. Guys, please look at this shape. It's not a best drawing, but I got it right here.
Oh, it's like this.
Look.
Oh,
Yeah,
okay.
yeah, yeah.
Oh, gotcha.
Right? So you have a parabola. You have a parabola.
What flavors are they?
Whoa.
Oh, it's a purple. Yeah, it's
no, but like there's an extra, but there's like a Pringle and another Pringle.
Oh, that's what Pringles.
Right?
Yes.
2 Pringles.
It looks like the original flavor combined with like double singular.
What flavor is blue?
Or like you know, you see those like.
No, it's just very old.
It's one of those.
Oh, okay.
Don't they make, like,
It oxidized.
That's bad. I don't know if they're putting in them. That's bad.
It's like a.
Pretty sure the FDA should get on that.
Look at the pink mouse.
Listen, my track pad broke. I'm really annoyed about it. The hardware just disappeared off the computer. I'm very annoyed.
All right. So, guys, we have a parabolic cylinder on top. Z equals y squared plus 1. And z equals 2 minus x squared. We say that these two, you call them Pringles, I guess. These 2 Pringles are rotated 90 degrees one to another because one has x squared, the other one has y squared. Also, by looking at the equations, guys, which one is on the top, which one is on the bottom?
The one on the left is on the top.
Wait, no.
Right is on the top.
Right on the bottom. Yeah.
Okay, you see two numbers, 1 and 2. Which one is on top? Which one is on the bottom?
The right one's on the
Yes, the 2 is on the top because the parabola over here is negative x squared, and negative x squared looks like this. And this is positive y squared. That's going to look like that. So clearly, this is the top, and this is the bottom. Great. The next order of business is to...
Are we just calculating?
Yes, we are calculating the volume. We are going to set up for this event triple integral, and let's use dz, dy, dx.
That doesn't have sharp edges, right? That's the only case.
Yes.
How do you know that?
Years of experience, dedication, and love for mathematics.
I'm just a little confused as to when you use the dr theta versus phi squared.
Well, one is cylindrical, one is spherical. Spherical is only when you have spheres and balls around.
Okay, so anything else as long as it doesn't have sharp edges. Okay. But it's
See?
I can't. I'm so excited at that really mediocre.
You'll be surprised how many people can figure it out.
You should have a higher standards. I just don't get how that's
You just told me opposite 2 hours ago.
How? I changed my mind. I don't know. It's hard.
Yeah.
But it is a straight edge that I would draw, even though I know it.
Excuse me?
Yeah,
That's how I feel.
that's like a number one rule. Doesn't know what it wants. All right. We have now the
Sounds like projection to me.
yes.
Okay.
Are we ready?
If you are.
Born and raised. Ready, yes. So we already know that the top equation is going to be 2 minus x squared, and the bottom is y squared plus 1. So that's the outer integral, that's the dz integral. We could actually do this as a double integral and then just use 2 minus x squared minus, in parentheses, y squared plus 1 inside as the integrand, so whatever.
For this one, does it matter what order you put one x in?
Well, it's symmetric, so let's see.
I think I know the yes.
Let's, we have to equal these two equations to see what's the region. So when I equal these equations, I get y squared plus 1 is equal to 2 minus x squared. I am going to push x squared to the left and get x squared plus y squared, and then move 1 to the other side, and I get x squared plus y squared equals to 1. It's a circle.
OMG.
Shut up.
Nice.
Where are the straight edges?
It's right there.
What?
They are sharp edges. They're not straight. They're sharp.
It means a piece of paper. A piece of paper has an edge here where it meets.
You want to see the sharp edge?
No.
So, what? I'm scratching myself. Anyway,
You told us at the beginning it was an SUS.
the sharp edge here.
You, how do problems do that? They meet, like, if you meet here, there's an edge here and an edge here. They just happen to be at an angle. Like,
all right. So our domain is a unit circle. And actually, this would be appropriate now to ask, since Stephanie had the question about this.
yes.
Since I know now that my domain over which this object resides, upon which this object resides, is a circle, what kind of mathematics should I use?
What are you asking?
What do I use in terms of to set up the integral over there? What type of coordinates? Yes. So we are going to use cylindrical coordinates because our domain is a circle. If you are not using cylindrical coordinates, you will have hell on earth to compute this.
Because spherical
It's not a ball. These are, yes. So I am going to set this up as rectangular coordinates so that you just can hate it. And then we are going to switch it into polar to make it easy. So, since I chose dx is like this, and dx clearly goes from -1 to +1.
So in this situation, you could switch dy and dx if you wanted it to be.
Yes. Mm-hmm. And then over here I have -1 minus x squared and positive square root of 1 minus x squared. So this is the setup for the integral in rectangular x, y, z coordinates. Now, since we do not want to, or maybe you do, I don't know, maybe you like pain. I'm not going to go there. If you are lazy, like I am, then you will immediately switch this into the cylindrical coordinates, because cylindrical coordinates will guarantee an easy run for this. So I will have dz, dy, dz, r, dr, d theta. There we go. And for our limits for d theta, it's the full circle in the domain, so 0 to 2 pi. The radius is 0 to 1, yay. The only issue that I have now is that my limits of integration for z are not given in our theta domain, and I have to fix that. So, no, we can't have any x's and y's, forbidden. So we are going to write 2 minus x squared is actually equal to 2 minus, and x is given as r cosine theta everything squared. So this thing over here is 2 minus r squared cosine squared theta, and the bottom is y, so that's going to be 1 plus r squared sine squared theta. So obviously now you don't have to compute any of the trig subs, because the polar coordinates conversion is making this problem much easier to solve. So now you just go integrate, sub some numbers, and you're done. Bueno?
Yeah.
Yes. Oh.
So as long as it's not like a rectangle, but it has somewhat curved use.
Yes.
And then it's a full sphere.
It's cylindrical, or a cutout of a sphere. We also know the equation with the secant, right? A secant x. If you have a ball that you cut to the plane, right, straight, in which case you are going to. Sounds good? Okay. All right.
I've been wondering around class, what happens to the wall? What wall?
That's where it's connected.
I know.
Connects right there.
What happened to the
I don't know. It was like this.
Oh, I didn't even notice the wall. Okay.
All right. That's well. That's that for today.
Okay.
See you next week.
What is it?